In the last video, we started talking about rigid bodies. Okay, and we defined first what a rigid body is. It's an object whose points, the points which make that object. Okay, the distances between those points are fixed; they do not change with time. That's the definition of it, and it's a good approximation if you are not interested in details of motion that happens within the object. Then we looked at the degrees of freedom it has, and in general, a rigid body has 6 degrees of freedom. That's what we evaluated. And while doing so, we first encountered linear configuration. So if you have a rigid body which has a linear shape, which is like a line, then it has 5 degrees of freedom. That's what we saw. And if your rigid body is pivoted at some point, meaning if it has a fixed point, then it has 3 degrees of freedom. That's what we saw last time. Let's continue further, and let's imagine that we have some rigid body. Okay, let's say this is our rigid body, and we have our coordinate system here. Okay, so these are our x, y, and z axis, and this is the origin. Okay, and think of any 2 points in here. Let's say I call this point as P, that point as Q. Okay, and let's say the vector which connects the points P and Q. Okay, let me put the Q there. Okay, this vector I want to call as vector R. Okay, so from here to there. Now let's say this body is moving as time goes on. Okay, so this vector R will be changing with time. So the vector which connects these 2 points will be changing. So right now it's in this direction and has this magnitude, and of course the magnitude is not going to change with time, but its orientation will change. It may orient at a later time in this direction, or the vector R could come out of this plane and be pointing towards you. Okay, so those kind of things will happen. Now I want to view this change in vector R as a transformation. Okay, as a linear transformation. The transformations will be linear. Let's see what precisely I want to say. So sometimes I will not use this vector arrow on R, and try to see if I can do a boldface. Is it easy? Yeah, it's easy, it's doable. Okay, so I'll use a boldface, and this is the same thing here, same vector which I have denoted there. Let me also okay, so by R I mean it's x, y, and z components. Okay, that is what I mean, and I am viewing it as a column vector right now. Okay, and as time changes, this vector R will become something else. Okay, and it will become some R prime. Okay, and that R prime will be related to your original vector R, this original column vector R, and there will be a matrix which will be multiplying that. Okay, it just says, see, matrix multiplication is a linear operation. Okay, and that is why you have it here. So this is how your R is going to transform. So your R is going to become R prime, which is A times R, and A is some matrix which we want to figure out. Okay, so let's do the very first thing which we would like to do is, let's say I look at R prime, or let's say R transpose R. R transpose R. Now R transpose R is just x square plus y square plus z square, right? And that's the square of the distance between these 2 points, and that quantity is not going to change with time, right? Because this is just the distance between these 2 points, and it's a rigid body, it cannot change with time. So this is going to remain fixed. as time goes on, as far as these 2 points are concerned, or any 2 points are concerned. Okay, but now we are saying this vector r is going to change into ar after some time. Okay, then what is my r prime transpose r prime? Well, this will be r prime transpose would be, I have to take the transpose of this quantity, which is r transpose. Okay, then you have A transpose. A is the matrix, that's good. Then you have this piece, r prime is A times r. So you get r transpose. Let me put a bracket around this just to emphasize that I'm looking at this quantity. You have this quantity. And as you know, this has to be equal to r transpose r, because the lengths are not going to change with time, right? The distances are not going to change with time between these 2 points. Okay, which means that A transpose A has to be identity matrix. So that's the condition which we have found by asking that the distance between these 2 points should not change, the points P and Q. Okay, and it says about the matrix A, one property of this matrix A, that A transpose A should be identity. And such matrices are called orthogonal matrices. Okay, so which means matrix A is orthogonal. Okay, that's the definition of orthogonal matrices, that their transpose. So if you have a matrix A and if it satisfies this, it means that its transpose is its inverse. Okay, that's what it means. So the transpose and the matrix are inverse of each other. Okay, that's what we have found. And one very important property of a matrix is its determinant. So whenever you come across a matrix, you think about its trace, you think about its eigenvalues, you think about its determinants. These are the things which we should pop up in our head. So let's ask about its determinant. Okay, if it's an orthogonal matrix. So let's ask the determinant of matrix A if it is orthogonal. Let's go to the next page. So what we want to know is determinant of orthogonal matrices. Okay, let's see. So let me write it down. You have A transpose A as identity, right? Now let's take determinant of both the sides, which means determinant of A transpose times determinant of A is equal to identity. Okay, that's the property of determinant. So product of two matrices becomes product of their individual determinants. And on the right hand side also I should have determinant of this. And determinant of identity is just 1. Right? You are multiplying all the diagonal entries in this case. It's 1. Now it is also true that determinant of A transpose, let me write it here. Okay, anyway. So determinant of A transpose is same as determinant of A. So that's what I'm going to use. So determinant of A times again determinant of A, which makes it determinant of A square, and that is equal to 1. Okay, this 1 is a number, not a matrix, which means our determinant of A could be either plus 1 or minus 1. So there are two possibilities, okay, for our matrix A, and it is that the determinant could be either plus 1 or minus 1. Okay, that's nice. Now, out of these two allowed possibilities, which one is true for our case? So our case meaning for the rigid body. You see, at this moment I have found out that if you are taking any orthogonal matrix, its determinant could be either plus 1 or minus 1. Okay, but it is not necessarily true that whatever possibilities appear here apply to our case, because we are looking at a very specific thing, okay, a body which is moving in time. Now I want to okay, before I say that, let me write which possibility we should choose. Should it be plus 1? Should it be minus 1? Or both can be here? That is what we are asking. Okay. Okay. So it's not difficult to understand what we should do, and it's simple to understand if we do it the following way. Now we can go from an initial location of points P and Q. So we start with our body in some configuration, point P and Q are given the way they are, and we ask, okay, and we ask what is the matrix A that takes you to its final configuration. Let's say it is called A prime B prime. So we start from, not A prime, P prime Q prime. So let's say we start from here. Let's say at time t equal to 0, you are here, and after some time t, let's say this thing is oriented like this. So the point P has moved here, the point Q has moved there. Okay, and their new locations are called P prime and Q prime. Okay, which means the body got displaced and got oriented differently. That is what it is saying. So it's here, and we want to know what is the matrix A that has taken us from here to there. So let's say this orientation was at time t equal to 0, and this is orientation at some another time t. Okay, and that is what we are asking. The matrix A of t, which will take us from R, meaning from PQ at time t0 to P prime Q prime at some other time t. Okay, or equivalently, we are basically asking what is this is the distance between the 2 points. Here is R prime and here is R, and what we are asking is how do you go from R prime to R. Okay, this matrix will depend on time because the object is going to move in time. Okay, at different times it will have different orientations and locations. Okay, and this is this matrix A whose determinants are in principle allowed to be plus 1 and minus 1. Now how do we fix this? How do we fix our choice? Okay, so it's easy. You imagine that you reach from your initial configuration to final configuration, which is given by A of t, in steps, in infinitesimal steps. Okay, so you don't take your object and turn the way you want to orient it. You make very, very small transformations. Okay, first step, second step, and third step, and a huge number of them, and then slowly arrive at that configuration. Okay, so it's just like going from point A to point B. I can say, okay, I jump from here to there, or you make small transformations and you reach at point B. Okay, now if I do so, then I am let's say I take the first I do a first infinitesimal transformation. So I don't reach to the final configuration, but I start from identity. Okay, at time t equal to 0, R prime is same as R. Nothing has changed, which means that A at time 0 is 1. is identity, right? Is that correct? Matrix A at time t equal to 0 is identity matrix, right? Because only in that case R prime will be R. No transformation has been done. So this is at time t equal to 0. Now think of an infinitesimal amount of time, delta t, okay, which has passed, and your A is now it has to be identity, no transformation at all, plus a small change because of the small transformation that happens in time delta t. Okay, so here you will have, in addition to identity, a little bit extra, and what that extra I will write as I don't think I want to use a symbol. I want to use a symbol. Okay, I will write some delta A here, and this delta A is an infinitesimal matrix. Okay, is that clear that this is the thing which we should write? Okay, so my matrix A differs by an infinitesimal amount from unity. And what do I mean by infinitesimal matrix? This means that the matrix delta A has its has as its elements quantities that are infinitesimal. Right? That's what an infinitesimal matrix would mean. Okay, that's good. Now let's look at the determinant of the matrix A after a time delta t. Okay, so I've done a little bit of transformation. I have not reached where I wanted to, but I've taken the first infinitesimal step, and I want to ask what is the determinant now of this new matrix. Okay, let it be A, but if you are having any confusions, you can think of it in more concrete terms like this. This is what this symbol A means here. Okay, so determinant of this would be determinant of identity plus delta A. Right? Is that clear? All I am doing is just taking determinant on both the sides in this equation. Now let's look at the right hand side. If that delta A is not there, the determinant of identity matrix is 1. Okay. Now because I have identity plus an infinitesimal matrix, then the determinant of this entire thing can differ or should be 1 plus a small quantity, right? 1 plus something infinitesimal, right? Because if this is not there, if this delta A is not there, then the determinant is 1. You change the matrix a little bit from away from 1, then the determinant should change at most a little bit away from 1, right? So you should get something like 1 plus, at most this can happen. Okay, so plus, so it should be 1 plus some infinitesimal number, which will be determined by the transformation delta A. Okay, that's good. And then you can do another transformation and again do this. So each time you do it, your value from the determinant value will change, can at most change by an infinitesimal amount. So you keep changing by infinitesimal amounts. Okay, but then you realize that no, that's not possible, because the only two possibilities that are available to you are either plus 1 or minus 1. So you cannot have 1 plus 0.0001. That's not allowed. So the only way it is going to work, or this will be consistent, is if this is 0, meaning the determinant never changes away from 1. it always remains 1. Okay, then it is fine. But if you say no, it can change a little bit, then you are in trouble, because you are not allowed to. Your determinant A can be either +1 or -1. You see, what you are really seeing is, because your transformations are connected to the identity matrix. Remember, at time t equal to 0, you are here. Okay, you are connected. You are continuously moving away from identity. And because of this continuous movement, you are going in small steps. Okay, because of that thing, you are finding that my determinant A has to be +1 for this rigid body motion. Okay, but in general, orthogonal matrices could also have determinant -1, and we will not talk about determinant -1 possibility at this point of time. It's not needed. So we have concluded that for our things, we are going to use determinant A to be +1. Okay. Okay, so make sure that you are able to understand, and the argument is fairly simple. But in my experience, when I'm telling this in the classroom, I have to several times repeat this, and students usually ask. But it is much simpler than it sounds at first. Okay. So good, and then we'll move on to the next parts of this discussion in the next video.